Yeah, so thanks very much for joining my talk. I'm going to talk about something light just before lunch. So compositional distributional semantics for modeling natural language. So what it's all about. So if you've ever added two word embeddings together, or you've used word embeddings as input to a neural network, you've basically applied a composition function to distributional word representations. So in this talk, I'm trying to give you some more background of what's going on in the research area, in that area at the moment. And I'll be focusing on why composition with word embeddings is actually a really useful thing, and why you should do it, maybe. But actually emphasize my talk on the current limitations of compositional approaches, because I think it's probably more important to know about the shortcomings of a method rather than where it excels. I'm sorry, it's probably dangerously academic at times, but shouldn't be too bad, really. As I said, it's something like just before lunch. So I'll start by just giving a short intro of what I mean by compositional distributional semantics, then talk about distributional word representations and why they're really, really good. Then go into some of the most common composition functions that are being used in academia and probably as well in industry, and talk a bit about their current limitations, and finish with just giving a brief insight on how compositional methods can be used baked into a bigger system. So what's semantics? Semantics is the study of the meaning of words and phrases in some language, and distributional semantics tries to achieve that by studying the co-occurrence statistics of different words in a large corpus of text. And then compositional distributional semantics tries to build longer units of text out of elementary distributional representations. So word representations are typically based on the distributional hypothesis, going back to Harris and Firth, based on the notion of similar words tend to co-occur in similar contexts. And you probably have heard the famous quote by Firth saying, "You shall know the meaning of a word by the company it keeps." And they also have a very, very long history in NLP research. It didn't just all start recently with word2vec. There was lots of other stuff going on much earlier, going back probably even to the 60s by Karen Spark Jones. And what we're trying to achieve is a continuous model of word meaning, where words are represented in a high-dimensional metric space. And this gives rise to a nice graded notion of similarity. So you can compare like dog to cat, and you'll find they are more similar than dog and car, for example. And more recently, we've started to make a distinction between count-based models and predict-based ones. So in a count-based model, you explicitly create a large co-occurrence matrix, keeping track of how often one word co-occurred with another. That's your kind of traditional PPMI-based word embedding. So also GloVe is based on a explicit co-occurrence matrix, and then they apply their matrix factorization model to it. This contrasts with context predict-based models, such as word2vec, which never explicitly builds this large co-occurrence matrix, but works implicitly on the kind of co-occurrence statistics. However, all of the models are usually based on the same underlying co-occurrence statistics in one way or another. And many of the kind of performance differences you see across tasks is often just due to different kind of hyperparameters. And why they're really cool? Because they really capture some very interesting linguistic regularities. And again, you've probably seen this example. So you take the vector for king, you subtract the vector for man, you add the vector for woman, and you get enormously close to a vector for queen, which is really, really cool. And you can measure the semantic similarity between different words on a continuous scale. And this really is a powerful concept, kind of figuring out that the concept represented by the vector for dog is more similar to cat than it is to tank or car or whatever. And the algorithm is unsupervised, it's unscalable to very large corpora. And it's also language agnostic, so word2vec usually doesn't care whether you feed it English Wikipedia or German Wikipedia or French Wikipedia. It will just happily crunch the data. And they're also kind of plug and play, so you can either download the pre-trained word embeddings, the Google News vectors, for example, or you just create your own using GenSim or whatever. And you add them to your NLP pipeline, and it usually just works very well and integrates usually quite seamlessly and effortlessly. And they're also really flexible, so you can use the off-the-shelf ones just as a drop-in. You don't really need them to train with whatever downstream task you have, but you actually can if you want to, if you need to. So word representations are really, really cool. They tick all of the boxes. They capture interesting information. They are unsupervised. They're language agnostic, so it can't get any better than that, really. So there's been lots of effort going into creating distributional word representations over the recent years, but at the end of the day, they're only single words. And most of language, usually, when we study, we are interested in phrases or sentences or full documents. So it would be nice if there was like the same off-the-shelf component that creates meaningful representations out of individual word vectors. That kind of integrates in a plug-and-play way with distributional word representations, offering also the same level of flexibility. Kind of you can use them as is, or you can just fine-tune the composition function for a given task. And at the moment, there's 4 major approaches. You've probably used 2 of them, or at least know about 2 of them. So the first one, the most simplest one, is just pointwise addition and multiplication of word vectors. The second one is based on the notion of formal semantics. A third one is anchored pack trees, which is really the most exciting one of all. And there's also just using them as input into a neural network and treating a neural network as your composition function. So pointwise addition, it's really, really simple. So you take your vector for big, you take your vector for seagull, you just add them together, and out you get a phrasal representation of big seagull. One of the major problems of this approach is that it's commutative. So we went to lots of length into creating those word representations, and then we just add them together, throwing away just lots of information, which is not really desirable. Nonetheless, they do represent an annoyingly hard-to-beat baseline. I've also seen that in my work. Just adding word-to-vec vectors together is just very, very difficult to beat, and it's really annoying. And despite their simplicity, they capture some very interesting patterns. So if you have your explicit PPMI-based co-occurrence vectors, and you multiply them together, then that actually creates a weighted feature intersection. So it only keeps the features that are common to big and seagull in the resulting vector. And the same is true for pointwise addition in neural word embeddings, which has been shown recently. And this achieves some things called contextualization, and which I'll talk about a bit more later on. And also, at the end of the day, the problem of commutativity might not so problematic for one task rather than another. So if you, for example, if your task is text classification, then you probably don't care whether you have race, car race composed in any way you want. It's probably the same anyway. But for others, like recognizing textual entailment, it's probably more important to get a kind of deeper insight into the semantics of a sentence. The second one is based on formal semantics, which is based on the notion of function application. So an adjective, for example, would be acting on a noun, and the linear algebra equivalent to a function would be a matrix. So you have a matrix for white and a vector for the noun car. You multiply them together to form the phrase white car. Probably the major problem for this approach is scalability, because the order of a word representation depends on its category. So we have a car, which is a noun, which is just a vector, so you could say it's a tensor of order 1. Then a matrix, an adjective is a matrix, which is a tensor of order 2. And then a transitive verb, such as catch, for example, in seagulls catch fish, would be represented by a third order tensor. So it really gets a bit out of hand here. Nonetheless, it's theoretically sound and linguistically grounded, if you care about that. It's based on Montagovian semantics. And it's actually a really, really neat idea, but it has some problems when it comes to putting the idea in practice. One of them being sentences of different length or different structure often end up with different dimensionality. So we've built a continuous model of sentence meaning, but then we have to compare like a third order tensor with just a vector, and it all falls down a bit. And it's definitely very, very difficult to scale beyond just very short sentences. So the next one's anchored pack trees. That's actually where my PhD is based on. So if you want to know anything about them, definitely talk to me later. They're exciting, they're brilliant. With them, we are leaving kind of our beloved vector land and move into a more structured graph land. So we represent words in nodes. So the colors denote different parts of speech. So a blue node would be adjectives, a green node would be nouns, and a red node would be verbs, for example. And the anchor denotes the current view into the data structure. And they're actually lexeme multisets, so it's not just a single word in a node, but there's more than one word. So in the node for white, you might find probably black and green and other colors in there. And the edges are dependency relations between those words that we find in a corpus. So our major problem really is sparsity, because we are counting co-occurrences, but we don't just count a word co-occurring with a word. We also take the grammatical relation between those two words into account. So the dimensionality of the space really, really explodes in some of my experiments. So having a 2 million dimensional space is just normal, really. And sparsity really is a problem. And instead of just reading in Wikipedia as it is, we first parse Wikipedia and then feed it through our algorithm. As I said, the nodes are represented by PPMI-weighted lexeme multisets, and the edges are represented by dependency relations. So the two structures, if you look at the white structure and the rabbit structure, they are kind of different. They live in a different space. So in order to be able to compose the two together, we need to do an additional step, which we call offsetting, and which really just takes the representation for white and kind of projects it into the noun space, and then the two can be composed together. The last and currently probably most successful and most popular composition functions are just neural networks. So you have your kind of lookup layer here with your word representations. Then the neural network actually is your composition function. So this can be your convolutional neural network or your bidirectional tree-based LSTM with attention or whatever people are using these days. And at the end, you usually have a downstream objective that you're going to optimize. So one problem for that is the transferability, because the composition function is kind of tied to a specific task, and plugging the learned model into another task often fails. So if you train your model on a text classification task, and then you want to do paraphrasing, then the text classification model probably doesn't work very well. The composition function is learned as part of an end-to-end model from the data, and it's really, really tailored to the one task you give it. And different tasks often require different kinds of composition functions, so it's not really a general purpose of plug and play, because you really need to retrain it with a given task from scratch every time. Although there's currently lots of progress being made for kind of multitask learning, kind of having multiple objectives, or working on domain adaptation, kind of adapting one net for another domain. And despite all of those tailoring and tweaking and the weeks of AWS time that you've spent, you often achieve only really small improvements over just adding word-to-vec vectors together. As I said, adding word-to-vec vectors just works really well and is really annoying somehow. It's nice too. So it's not all that bad, really. All major approaches that we're currently using, they have some issues of one form or another. And composition functions, unlike word representations, are not yet such a nice and general purpose drop-in. But they are reasonably practical and useful. I'm sure many of you have used them. But there's definitely more problems, which is how do you measure which one's the best? So evaluating composition functions is quite hard, and it's probably the Achilles heel of current research. There's not really a good way to determine which composition function is better than another. And if you've been to Miro's talk on labeling gold standard data yesterday, or on Mapti's talk on evaluating topic models, you probably do know that evaluation is really important. For compositional models, it's either based on a phrase similarity task or some sentence similarity task in comparison to human judgments. And similarity for humans is already quite difficult on just the word level. And the task doesn't get any easier with more words. Second way models are evaluated is just on some downstream task. But there's just too many factors that can influence performance, so it's not really a clear picture of the composition function itself. And it is definitely difficult to design a good task because we need to figure out what we actually try to measure. Is it the generality of a composition function across many downstream tasks without any retraining of a model? Or is it a specific one, so the continuous model of word meaning on the sentence level is probably very close to paraphrasing? Or is it more interesting for entailment, kind of what inferences can you draw from a sentence representation? Or is it actually really task specific? So we might figure out that just training a neural network on one downstream task is good enough and we can't do any better otherwise. But there's actually a few more issues, so taking a bit of a more global point of view. Even if everything would be working perfectly, there's the question, what does a sentence actually mean? So if you imagine your word co-occurrence space, you can pin down some nouns over here and some adjectives over there, and that makes sense, but how does this work for sentences? Where should they be? And the longer a sentence becomes, the more difficult it becomes to determine what the sentence actually means. So I've kind of copied out a random sentence from a Wikipedia article, and it's about some battle, probably not very significant, in the 1700s, somewhere in Britain, and you can ask a lot of questions about that one sentence. So who fought whom, when was the battle, where was the battle, who won the battle, and it's very difficult. So the question is, should a sentence like this really be encoded in a single vector? Are 300 dimensions of word2vec or whatever really enough to kind of encode all of the gory details of that sentence? One answer to that is by Professor Ray Mooney. He said you can't really cram the whole meaning, the meaning of a whole flipping sentence into a single flipping vector. And the problem is also not just philosophical, it's also very practical. Because if you use an intersective composition function in your explicit PPMI co-occurrence space, you might just run out of features at some point and end up with an empty vector, which is pretty meaningless. On the other hand, if you kind of add those vectors all together, you accumulate too much information, and that one vector is now kind of similar to pretty much everything because it encoded too much information. Okay, so I've talked a lot about kind of why composition is flawed. It actually is good for something as well. So it leverages existing resources effectively. So word representations are really great. They encode a lot of meaningful information in a very limited amount of dimensions in space. And composition also achieves kind of contextualization. So if you, usually in any kind of text, you have some issues with polysemy, like the word bank can mean a riverbank or a financial institution. And if you only have a single vector representing bank, then you actually create a weighted sum of the different usages. So if you see the financial institutions, and more often the kind of vector is more pushed towards that way as opposed to the riverbank meaning. And if you compose that, composition has a sense discriminating effect, so you kind of recover some of the sense-specific information. And with some context, polysemy might actually not be such a huge problem at all. And this even works for simple composition functions, as we've shown in a paper earlier this year. So if you just take word2vec and you add river and bank, and you inspect the nearest neighbors, you kind of get into a riverside neighborhood. If you compose bank and account, just by pointwise addition again, you kind of get into a financial institution neighborhood. So this is really nice because you don't have to kind of create sense-specific embeddings. You can just create one vector per word and then use composition to kind of leverage that. And it's already been used successfully in many different systems, ranging from parsing, machine translation, sentiment analysis, and so on. But it's not yet a plug-and-play and general purpose. And for the remainder, I'll briefly talk about two kind of use cases of how composition can be used as part of a larger system. One of them is going to be aspect-based sentiment analysis, and the other one being question answering. So in aspect-based sentiment analysis, you're not just interested in the overall sentiment of a review, but in some very specific aspects. So for a camera, you're probably interested in the lens or the battery or the weight. And if you just care about the full sentiment review, then some kind of bag of words plus TF-IDF and an SVM at the end is going to be good enough, and it's definitely going to be hard to beat. But if you care about knowledge on the sentence level for specific aspects, you need a more fine-grained understanding of what is going on, and can give you a more detailed insight of what makes a review a 3 or a 4 out of 5 instead of a 5 out of 5. And that's quite an interesting problem, because if you have a review that's 4 out of 5 stars, that's positive. The product is being liked, but there was something that was kind of wrong with it. And you can use composition to kind of figure out what was wrong and kind of illustrate that. And these guys, Al-Gunay et al., they create a compositional representation of each sentence in a review. And this gives them like the continuous representation and continuous scale of similarity between different parts of a sentence. And what they do is they create multiple representations per sentence. So if you have a sentence like, I like the lens, but the battery was crap, they'll kind of extract lens with its surrounding context, like lens, and same with battery crap. And then they'll just compose the two together to kind of get a notion of what is being said about batteries and lenses. And so composition is quite a good way to identify common issues that are being talked about in many reviews. And as a bit of a longer shot, it can provide an insight of what individuals look for in a review. So if I travel a lot and I say, well, the camera was nice, but it was much too heavy, then this can give insight that I really care about the weight of the products I buy. So somebody please recommend me light stuff. For question answering is another way how you can use composition with distributional semantic vectors. So traditionally, it's been set up as a kind of information retrieval problem, where the goal is to retrieve the most relevant answers to a given question. If you have n answer candidates, then the most relevant is usually the right answer. And is a good way to exploit distributional representations of answers and questions. And composition can really leverage their commonalities and figure out what kind of semantic content they share. And again, composition here achieves the contextualization of content words and acts as a mechanism to integrate all of the knowledge from this individual words into a longer phrase. So if you have an example question like, what was the name of the fascist dictator of Italy during the Second World War? Italy is quite polysemous here. So you can mean the geographical sense of Italy, like I'm going to Italy this summer, or the political sense of Italy, kind of Italy urging the European Union for help in the refugee crisis, or the kind of sports sense of Italy, kind of Italy being defeated by Austria in the World Cup. Why are you laughing? That will happen. So, and you have 3 answer candidates. And by composing Italy with fascist dictator and World War II, you kind of get into a neighborhood that's kind of historical, political, and you would assume that a vector representation of the named entity Benito Mussolini would create enough overlap, at least in comparison to the other answer candidates, to kind of get you the right answer to the composed question. Yeah. And obviously, this composition is not just restricted to symbol named entity-type questions and answers, but can also be applied to more complex answers. And already almost at lunch. So distributional word representations are really great, and composition is a good way to effectively leverage these existing resources. Composing word representation, it does work, but it has its limitations. And different composition functions, which I've presented, have different shortcomings. So on the one hand, you have like the unsupervised and very general methods, just like adding. And on the other hand, you have supervised and very specific composition functions, like a neural network. And a very important issue is how to evaluate them, which one's really the best. And it's a very hot topic. Probably as we speak, there are multiple papers posted on arXiv that are talking about composition in one way or another. And it's lots of progress being made pretty much on a weekly basis almost. And yeah, that's it. So thank you.
Thanks for the talk. You mentioned on one slide that people are starting to take pre-trained models and gear them towards a specific task, like a pre-trained Google Word2Vec. I wondered if you could mention maybe how people are doing that generally.
Hang on. You mean like the multitask learning or domain adaptation?
The general method of adaptation, like be it single or multitask. I've seen it done in speech recognition, for example, where they can take a pre-trained speech recognition model and then somehow put like a last layer, which is really good at medical terms in a neural network. Is there yeah.
That's usually how it's been transferred. So usually you take some of the hidden layers and plug it into a different task. And then you usually just fine-tune the task. So these guys, Mu et al., have shown this works really, really well if you have kind of semantically related tasks. So if you kind of have a classification task and maybe a sentiment analysis task, and you use the learned hidden layers for sentiment analysis, it works really well, and you only have to do a bit of retuning. But if you use like the transfer from text classification to paraphrasing or parsing or whatever, then it fails because the two tasks are not too much related to each other.
Thank you.
Interesting talk, thanks. It's just more curiosity. I was wondering if you ever work with a simple model which you still sum the word embeddings, but you have an order on which you do the sums, and the order is based on the hierarchy, on the syntax parsings. So, and if you play with it, and what were the results? Because I have a feeling that just these simple things might work very well.
Would you still just add them together, or?
Yeah, but for instance, you take the order, you take like two words are connected in the syntax parsing, so you sum those two. Yeah. Then those two are connected with another one, and then you sum the result of that one with the other one, just following the structure of a syntax tree.
But if you sum them, they would. So do you mean a weighted sum, or do you mean just?
You can also, you can also use the weighted there. Yeah. I think Richard Soccer did something that's similar for
exactly,
sentiment analysis.
That's the recursive network that he used to kind of create a composition all the way up to a sentence from like individual words.
Yeah, but I meant in the sense you don't need to use the network at the end, but just summing them based on the on whether they are connected or not through
that's definitely a good way. That's probably a good intermediate between like plain adding and a full neural network.
Yeah, and you need not to over-engineer or to complicate much, and probably already have some better results. Thanks.
Yeah, thank you.
maybe I just missed it, but where in this picture are topic models or latent semantic technologies? I'm kind of wondering whether, I mean, there is an added value from your point of view to represent words as higher dimensional concept, whatever that means?
So latent semantic analysis, I think you usually also add them together, so they would kind of play in the additive space. Topic modeling is a bit like in between there, because you have like the kind of probabilities over topics and the adherence to different documents. So yeah, they are a bit out of those four that I represented.
Hi. Maybe a stupid question, but I was wondering with the composed semantics, is there an idea of whether you need more dimensions than for the word embeddings? Like in word embeddings, I guess the sweet spot has been found to be about 300 dimensions. So especially with the more advanced composition method you presented, is there an idea what sort of a sweet spot is there, what you end up with?
No, so at least I haven't found one yet. I think in machine translation, people have kind of settled on 1,000 dimension as a bit of a sweet spot, so because there needs to be just more room for information to be encoded. But generally, no, we haven't found like a really good number that works well, like the 300 for word representations.
So that's less of a question and more of a follow-up from the previous one. There's been a lot of work, most notably from, say, Marco Baroni's group, where they don't really have a fixed dimensionality for every word, but rather they have like a vector for nouns, and then verbs would be two-dimensional as matrices, and the intuition being that if you want to do composition, say, as matrix multiplication, then you want the verb to be a more complex thing because it needs to take arguments. So the matrix multiplication is effectively a function that takes two nouns. And same goes for adjectives. So the way to add more dimensions is not by just having a single vector that's longer, but by going into a matrix or a 3D tensor.
Yeah, you mean like the formal semantics-based approach to composition?
Yeah.
Or, yeah.
So my question then that follows from that is, how do you see all that kind of very theoretical work coming in from physics and like Bob Koch's work? How do you see that fitting with the neural network trend?
Well, those people like Baroni and Bob Koch and stuff, they've already moved on to neural networks now, more or less completely. So I still think like representing words, adjectives as matrices and kind of verbs as tensors, it's a neat idea to kind of integrate semantic composition based on a Montagovian kind of point of view into distributional semantics. But it doesn't scale very well because the kind of matrices you need to learn get out of hand, and you need to learn different matrices depending on whether a noun is in an object position or in a subject position. What was your question with regards to how it relates to neural networks? Or
do you see the two as incompatible, or do you reckon there's a way to put those two together somehow and say maybe use a neural net to learn the tensors for a more Montagovian semantics?
That could work, yeah. I mean, the matrices they used are trained based on stochastic gradient descent and kind of usual optimization techniques that you use in neural nets anyway. So probably yes. So maybe neural nets can help create better adjective matrix, for example.
Are there any other questions? I have one. In your overview, you gave 4 approaches. One is missing, namely the one that was proposed by Kwok Lee and Thomas Mikolov.
You mean doc-to-vec?
It's Thomas don't like that word, so it's called paragraph vectors.
Paragraph vectors, yeah, sorry.
aka doc-to-vec. Did you do it on purpose? Leave it out?
A bit, yes.
Why?
It didn't so well fit into the clean story because I'm not an expert on paragraph vector, so I can't comment too much on it. But it plays in the neural networks field because they learn like a paragraph vector with the paragraph ID, so optimizing some downstream functions. So it's kind of in the neural network field, I would argue.
Okay, if there are no other questions, then let's thank the speaker again.
Thank you.